Hello, thank you for joining my virtual dissertation talk. First, I'd like to start with a big thank you to many people who I encountered during my graduate school journey. I felt my journey was quite difficult, and I would not have made this far without them. Talking about difficult times, sometime after the pandemic lockdowns, my advisor Maya let me borrow Temi, which is like an Alexa on wheels. We have been treating it as a toy for my son, but in a post-pandemic world, I can imagine how we might have to rely on a robot like this for everything, such as entertainment, remote schooling, and maybe even at-home childcare. So, what would it take to create such an educational application today? First, there needs to be enough behaviors or content for the robot. For example, there should be as many study materials as there are books for e-reader like Amazon Kindle. But involving programmers to create every such behavior is not a scalable solution. An alternative solution is the end-user programming, which is letting everyday service workers like teachers to program the robot by providing them with user-friendly programming tools. One of the major problems with interactive robot behaviors created using an end-user programming tool is that they are not adaptable. In addition, such programming tools are usually not expressive enough to let end users tweak interactive behaviors on their own. For example, a teacher might want to change the robot's use of body language, the loudness of its own speaking voice, or its navigation speed to increase the engagement of the teaching material for each student, but this is not easy to do today. My research goal is to facilitate creating interactive robot applications and behaviors with human-centered design and non-expert-friendly programming systems. I envision one day creating educational content for future home robots will be as easy as creating teaching material slides for classes today. Today, I'll present a series of work I've done towards my research goal. At high level, I'll first briefly share our past experiences with creating interactive robot applications and behaviors in the real-world settings to feel out the needs and challenges of involving non-experts to program the robot. And then, I'll present more recent work on addressing the two main problems we identified. So, the first part of the talk is about our work on creating information-gathering robot applications in commercial spaces. A large portion of running a business in commercial spaces like offices and retail stores is about gathering information. Think of inventory checking. And we thought autonomous mobile robots could help with such information-gathering tasks. From 2014 to 2015, we designed and evaluated an experimental application that lets people ask any questions related to the current state of the building. The robot then responded by navigating to a location, taking and sending back a picture relevant to the user's question. We'll not go any further on this project, but I'll just mention that in 2019, startup companies like Cobalt Robotics and Bosanova Robotics successfully raised funding for building robots for security and inventory management purposes. Customer feedback is another type of information that robots in commercial spaces can collect. Some robots are more interactive, and we thought the robot's embodiment and its role as a helper between hotels and guests could make the robot a potentially effective tool for gathering customer feedback. To explore this potential use case, we conducted formative studies consisted of need-finding interviews and user surveys to identify and gather the user requirements. Based on the collected data, we prototyped applications and evaluated them in the context of use to verify the feasibility and extract design implications based on the findings from long-term deployment evaluations. We highlight the following findings. Hotels would love to catch the unhappy guest on site, for example by getting notifications on receiving negative ratings on the robot, and spread the good news, for example by posting positive ratings online. For guests, Convenience and privacy were the top priorities. Regarding privacy, while most wanted hotels to know their opinions, some expressed that they don't want to be seen by staff members while giving ratings to the robot. More generally, we suggest keeping the interactions short and delightful, using movement judiciously to avoid annoying guests and staff members. And if possible, we suggest tailoring interactions to each guest group to meet their unique requirements. Next, I'll briefly present our work on designing a programming system for interactive service robots. One of the lessons we've learned from the previous work is the customization needs. For example, in our information gathering robot use case investigation work, we observed that the types of questions people asked to the robot had a long-tailed distribution, and it was not possible to pre-program the robot to handle all user requests upfront. As for the customer feedback collection application, hotels expected that more guests will respond to the robot if they could customize the robot's behavior to the types of the guests. With the goal of enabling non-roboticist service workers to program the robot, we asked ourselves the question, how should we design a programming system to support creating interactive behaviors for service robots? Particularly, we were interested in better understanding the programming requirements and the potential challenges for non-expert users. We investigated this question by taking an iterative design approach with an interactive service robot platform, the Saviok Relay. First, to better understand service workers' intended use cases in commercial areas, we interviewed groups of target users such as an airport and hotel staff members. We learned that most desired use cases involved interacting with visitors. We prepared an initial programming system by extending an existing system for programming the relay robot called Custom Programs. Custom Programs is a block-based visual programming interface wrapping a scripting language with a set of predefined robot actions made available to programmers. We started with Custom Programs for its battle-tested usability for non-experts. We then prototyped interactive applications like a greeting airport passenger application with service workers and deployed them in the field to mainly observe how guests interacted with the robot. Based on system logs and observation notes, we refined the programming system. We repeated the same step once more. This time, we let the service workers lead the programming of the robot and focused on observing how they use the programming system. We summarized the key extensions we made to the custom programs throughout the design process. First, we added perception primitives like getDetectedPeople to enable more proactive behaviors. We also added interruptible primitives like goToUntil that makes the robot navigate to a goal until a certain event like screen touch happens to enable more reactive behaviors. Finally, we added asynchronous primitives like startSound that plays a sound without blocking the main process to enable more expressive behaviors, for example by layering multiple robot actions. All the extensions essentially enabled creating more interactive behaviors. Overall, we highlight the following findings. Interactive robot programming systems should allow expressing concurrency for creating rich interactions with ease. For example, the key extensions I just presented in previous slide are essentially added to support programming robot behaviors with concurrency. In addition, the systems should let users change low-level behaviors, like movement. During the field study, one of the main reasons that required an expert programmer in the field was to change the low-level details of the program that caused problems like moving too fast for passengers in busy area. We'll revisit these issues in upcoming parts of the talk. While working with non-expert service workers, we noticed known problems in end-user programming such as challenges with programming from the scratch and debugging. The non-expert users also faced challenges in writing readable and reusable code. It was interesting because these problems occurred naturally as many users never refactored their programs and used them for multiple important internal demo events. Finally, many non-expert users had a hard time creating engaging interactions. A lot of them created dull text-based interactions that doesn't follow social norms of humans. I did not further investigate these challenges for my thesis. However, I believe they are interesting and important problems to address in the future. I'll now further discuss supporting concurrency in the context of programming interactive robots, which is one of the requirements we just identified. The extensions presented in the previous work enabled expressing concurrency. For example, an asynchronous primitive start sound enabled layering multiple robot actions, and an interruptible primitive goTo until touched enabled executing an action while monitoring an external event. All additional primitives we introduced is one possible way of supporting concurrency. The natural questions to ask then are, is what we did the right way? And what are the other ways to supporting concurrency? In this part of the talk, we asked the underlying question of how should we design a concurrency interfaces for block-based visual programming in the context of programming interactive robots. We focused on block-based visual programming mainly because many non-experts find it familiar and it is widely used and studied for programming robots. Typical block-based visual programming interfaces wrap a procedural scripting language like Python and provide a set of robot actions as functions. Hence, we are assuming the same programming environment for our work. Let's consider creating a visual programming interface for this simple tabletop robot. Let's say the robot can interact with humans by speaking and recognizing speeches, making gestures, and displaying and sensing things on its face screen. To create a programming interface, we first needed to define an interface for working with this robot. Here is a set of available robot actions defined as functions. A robot action function can be blocking, meaning it blocks the main program until the action is finished, or non-blocking, meaning it triggers an action and immediately moves on to the next part of the program. For example, calling the blocking save function will pause the program until the robot is finished speaking, but calling the start save function won't pause the program. We also define sets of events relevant to programming the robot. First, we categorize the events into two groups, externally triggered and action triggered. For example, externally triggered events are ones caused by the environment, including humans, like the speech detected event. The action triggered events mark the end of the action, which comes in handy when using non-blocking action functions. One way to make use of these events is by registering a callback function as an event-driven programming paradigm. We introduce a generic when function for this purpose. Another way is blocking the main program until an event occurs, for example, to create a reactive behavior. We introduce a wait-for function for this purpose. An event can be converted into a state, for example, by memorizing the last emitted value. We then introduce state accessors like getLastEventValue to read a current state value, which is yet another way to work with events. With the proposed way of categorizing robot APIs, we now define our three concurrency interfaces called Async, Callback, and Wait For. Async enables concurrency using asynchronous procedure calls, which represent a traditional approach for enabling concurrency in an imperative programming language. Think of the interfaces used in socket programming. Callback represent event-driven programming paradigm, which is common in UI programming languages that involves a lot of interactions. Finally, wait-for is inspired by event synchronization utilities involving promises, and they encourage writing concurrent code while staying in an imperative mood. The three interfaces can be viewed as three different configurations of enabling or disabling the categories we defined for robot APIs. Let's say we want to implement the following example robot behavior. We want the robot to start saying something, and at the same time monitor if human says something. If either the robot finishes speaking or the human interrupts the robot by saying something, then the robot should display on standby. For async, all actions are non-blocking, so we'll have to use a loop and state accessors to create wait behavior by constantly looking up either is saying or last detected human speech state has changed to move on. For callback, it provides when construct, so we'll have to use a callback function finish and register it in when with speech detected and say done events so that the callback function can be called when both of those events occur. Within the callback function, the logic for not repeating itself, for example, by saying on standby twice is implemented. For wait-for, it provides a program construct wait-for1 that takes two blocking functions like say and wait for human speech detected. So we'll just use that to block the main program until one of the events happens. To compare three interfaces, we needed a way to describe desired concurrent robot behavior. For this purpose, we defined concurrency patterns with 3 event combinations and 2 compositions. The concurrency pattern used in the example is action and event and wait for all. One of the ways we compare the 3 interfaces is by conducting an online user study. We recruited participants with some programming experiences to keep the duration of the study about an hour and a half. We wanted to know which interface was the easiest to use, so we asked participants to implement a robot behavior and measure the score calculated using the rubric we prepared for the given task. We also measured the conciseness of the participant's program by using the number of blocks used in the program. Here is a screenshot of UI for participants to work on the given task. Here is the task description that contains 3 concurrency patterns, as we defined. We observed that participants who used the wait-for interface did the best, while the ones who used callback did the worst. In terms of conciseness, again, participants who used wait-for produced the most concise programs, but this time those who used async created most verbose programs. We became curious why callbacks were hard to use. Investigating participants' program, we noticed that many participants choose to program the task behavior in an imperative mode, for example, involving loops to constantly checking the changed states. However, we originally expected them to create a more trigger action-like programs. In summary, we investigated the question of designing concurrency interfaces for block-based visual programming in the context of programming interactive robots. We first presented our approach to categorizing robot APIs with concurrency in mind and identified common concurrency patterns in robot programming. Based on our categorization, We presented 3 distinctive concurrency interfaces that are representative of existing interfaces. Finally, we compared the 3 interfaces for their ease of use and conciseness with a systematic evaluation and an online user study involving non-expert programmers. We observed that the interface with simple event synchronization utilities produced more correct and concise programs. One of the requirements we identified earlier is a way to easily modify the low-level behaviors of interactive robots. I'll now present our work focusing on helping non-experts to easily tune program parameters such as perception thresholds and timing parameters for improving interaction quality. Based on our experiences, we learned that non-programmers should be able to modify parts of the robot behaviors like reaction timing that are critical for the interaction quality. But exposing low-level APIs to non-programmers is not an option. In fact, parameter tuning is hard even for programmers. They need to feel out uncertain limits, scale, sensitivity, and consequences of changing each parameter. In addition, testing HRI programs require human users, which makes the parameter tuning even more challenging. Because of the parameter tuning problem, most end-user programming tools that are widely used today almost always provide a text editor to let users to modify the actual code of the program. In this video, the thresholds for telling the robot to stop approaching the detected person was not set correctly, and the robot was kept moving towards the person even when it was within the distance that person can comfortably interact with. Although the person left the robot, if he really wanted to engage, he could try to initiate the interaction by tapping the robot and hence correct the robot's erroneous behavior. Inspired by this observation, we propose an iterative process that incrementally repairs program parameters using the feedback provided by robot's user on the fly. It starts with a programmer writing a transition function program of a finite state machine representing the robot behavior. We introduce a domain-specific language that lets programmers to use holes in place of low-level details such as sensor value thresholds and timing parameters specified as probability distributions. When ready, the program is executed on the robot and the robot's user interacts with it. The system collects the interaction trace such as FSM inputs, outputs, and states that are occurred during the interaction. If the holes are set to bad values, interaction breakdowns are likely to happen. For example, just now the robot should have waited for the user but moved on to the next question. The user who noticed the problem tapped the Go Back button to fix the error and continued interacting with the robot. We assume a recovery mechanism like providing Go Back or Next buttons, as shown in the video, is possible. Once the interaction is over, the programmer can spot the breakdowns by checking the robot's user input and correct the mismatches between the expected and recorded state trace to produce a corrected state trace. Alternatively, such corrections can be derived from users' recovery inputs, freeing the programmer from remaining repair process. The repair algorithm now uses the corrected state trace to improve the program by estimating the hole distributions. The process is iterative, and hence our repair algorithm uses a Bayesian inference technique to efficiently update the distributions as more corrections become available. Here is our iterative Bayesian repair algorithm. It starts with a program sketch K and a set of distributions over hole variables theta. For each iteration, it runs the program with current hole values and records traces of FSM inputs I and states O. The corrected state trace O hat is computed by using another algorithm, implicit state correction, which essentially derives corrections from the recorded traces and looking at the program structure in the program sketch. The core step of finding a better set of holes is done by taking a map estimation on posterior distribution over the holes. The posterior distribution is computed using the overlap between corrected state trace and candidate state trace as likelihood function. Finally, the prior for the next iteration is set to the current posterior to keep the iterations going. The three core benefits of our approach are: first, it allows programmers to use distributions to describe uncertain parts of the program. Second, it frees programmers from having to be in the program maintenance loop by constructing a part of repair objective from the data collected from the interaction. And finally, it makes the algorithm efficient for online setting, that is, naturally reflecting our target use case scenarios. We evaluate second and third points as a part of our evaluation. To systematically evaluate the proposed Bayesian repair algorithm, we created human simulators for sampling a large number of FSM input and ground truth state traces. We also created a more traditional search-based repair algorithm to use it as a baseline method. We then compared the two algorithms over 3 social robot interaction scenarios over 5 iterations. We measured interaction quality of each algorithm using percentage overlap between ground truth and repaired program's state traces. We also measured the algorithm speed using repair time. Our results show that the proposed algorithm performs nearly identical in percentage overlap measure in all 3 scenarios. In terms of the speed, it outperforms the baseline as the Bayesian repair time remains at constant, while the baseline repair time increases linearly over the iterations. To test the full pipeline, we conducted human experiment with 10 participants and a custom-built social robot. The participants interacted with the robot over 4 iterations. We measured the interaction quality using objective measures such as the number of interaction breakdowns and the total interaction duration in seconds, and 3 subjective rating questions designed to measure the perceived fluency of human-robot interaction. Our objective measure results show that the number of breakdowns and the total interaction durations generally decreases over the iterations. As for the subjective measures, the average ratings of 3 perceived fluency questions increases over the repair iterations. We present one example from our qualitative results. The video shows one participant participating in the question and answer interaction scenario. When the participant stopped speaking, the robot failed to detect her floor management gaze inversion and moved on to the next question, breaking the interaction and leaving her seemingly frustrated. After the 2 repairs, the program was able to detect the participant's floor management gaze aversion and waited until she completely finished answering the question. We present more experiments and analysis in the paper and believe our approach is useful for helping non-roboticists with creating natural human-robot interaction. That covered the last part of the talk. Today, I presented a series of works I've done towards enabling non-expert service workers to easily create interactive applications for robots in real world. And here are directions for future research that we feel important and interesting to investigate. In our research, we started by gathering the requirements for robot programming systems from the field experiments, and then moved on to working on solutions. In the future, I'd like to start from designing a programming language or mathematical model that meets the requirements gathered in our research to find a representation that best captures the nature of human-robot interaction programs. As for building HRI program authoring systems, I believe employing program synthesis techniques could address the challenges non-experts experienced using our programming system, such as the burden of creating the full programs from the scratch and creating interactions that follows the social norms of humans. Finally, more work in designing intuitive UIs for non-experts and evaluating them with long-term use cases in mind will be necessary. In summary, I presented our research on non-expert friendly programming system for creating interactive robot applications and behaviors. In the spirit of human-centered design, we first gathered experiences with creating interactive robot applications and using robot programming systems with non-experts and reported our findings regarding the user requirements, challenges, and design implications. We then identified concurrency issues and parameter tuning as the two main problems to address, proposed our approaches, and demonstrated the usefulness by conducting various experiments. I believe there are a lot of opportunities for using interactive robots in a post-pandemic future. For example, remote teaching or at-home elder care may be assisted by personal robots at home. I hope our research can help everyone who sees the benefits of using robots to be able to explore such opportunities to improve our daily lives. Thank you.